Hey guys, what's going on? So today we are going to be talking about the total Lie algebra for two different representations. We're going to talk specifically about what these representations are, them being the 1/2 zero representation and the 0 1/2 representation. What we're going to find is that these representations represent spinors. Okay, we're going to spend a couple of videos investigating exactly why these representations represent spinors. And this will give us some insight into exactly how we can think of spinors as representations of, or objects that representations of the Lorentz transformation act on. So let's get right into the video. But before we get into the video, make sure to hit that like and subscribe button. And also, if you want early content, make sure to find or go onto my Patreon page, and you can get the content there as well. Now let's get into the content. All right, so we are talking about the total Lie algebra for these two guys right here. So what we're going to do is we're going to find each one individually. So this video might be a little bit long. But these two guys are representations, again, of our Lorentz transformations. So just as a reiteration, our Lorentz transformations, again, are things or matrices that act on four vectors, and they're very good at describing space-time. It's in special relativity for us. All right. What we then found out was that there's different representations of this type of transformation, right? So the 4x4 matrix representation, for example, is a representation of the Lorentz algebra. However, there are other matrices that do the same thing, right? They don't really do the same thing, but they fall within the category of being a Lorentz algebra because they have that Lorentz algebra structure to them. Okay, and we're gonna look at this right now. So recall again that we had our transformations that preserved our Minkowski metric. And these transformations were represented by 4x4 matrices. Okay, so the 4x4 matrices, again, those were the generators those are our SU2 generators, right? But they were 4x4 matrices. Okay. And what we found out, what you can do is you can take those generators, again, so these are the generators, just as a reiteration, you could take these generators and you could find out that these generators, or these matrices, obey the following algebras here, right? So we have our rotations, a rotation with a boost, and our boosts, right? And this is the relationship between, these are all the relationships or commutation relationships between these guys right here. So the question becomes, so this isn't Lorentz algebra, right? Remember, the Lorentz algebra is one commutation relationship and it's closed, right? So this is Lorentz algebra, but because we have boosts and rotations, together they don't form a Lorentz algebra. They form sort of this broken form of Lorentz algebra where you have what looks like Lorentz algebra here, but then these two guys are not really closed. They're not really algebras. And the reason for that, again, is because, well, this guy here, this is a J, this is a K, and we have a K on this side. So there's some asymmetry going on here, and KK, but then we have a J here. So again, that's why these two guys aren't closed. This guy here looks closed, right? This is our rotations seem to be closed, but when combined with our boosts, things sort of break apart. So, and that's what I'm saying right here, right? So this algebra, the Lorentz algebra, does not form a group. Given these boosts and these rotations, we do not have a group. So we are going to combine them in a special way to make them elements of a group. And how are we going to do this? Well, exactly like this. So this is a new matrix, but it encapsulates a rotation and a boost. So for every matrix, so how many matrices do we have here? Well, we have 6. right? You might think, well, why not 3? Well, there's 6 because we're defining this plus and minus sign up here as well, right? So we're going to have an n plus 1, we're going to have an n plus 2, and an n3 and a plus up here. And then we have another set of independent matrices like this. So that's 6 of them, right? That's 6. These are 6 generators, okay? And these guys, what you can find out, I'm not going to do this explicitly because we kind of want to make these videos seemingly short so you don't lose interest. But these guys, you can find out, form a Lorentz. They close our Lorentz group, right? So this is exactly what we're looking for, and this here is an SU2 Lie algebra. This is what we found to be true for our spinor, or not for our spinors, but for our Pauli matrices. Okay, interesting, right? This same structure for Pauli matrices. What's going on here? This is going to be the thing we always want to keep in the forefront of our mind, is the way these representations are sort of linked together is through this form of a commutation relationship or an algebra. Their algebras are the same, essentially. Their Lie algebras are the same. This means we can find other representations for our Lorentz transformation, right? Because, so if we could find any group of matrices that obey this rule, then what's stopping us from thinking that those other matrices are that they also are Lorentz transformations? So that's the mindset we want to have here. It's a little bit abstract to think about, but we always want to keep this guy in mind here when we're doing this kind of math. And when we get into things like isospin, quarks, leptons, and all that kind of stuff, we really want to keep the foundations at the forefront of our mind. This being probably the most important foundation we want to keep at the forefront of our mind. So, just as a recap also, so this is what we came up with last time when we were talking about how we're going to label these representations, right? So we have a one-dimensional representation and a two-dimensional. Then we get 3- and 4-dimensional representations also. We're going to focus really just on our one-dimensional case and our two-dimensional case for right now, and for the foreseeable future of these videos also. And so let's go ahead and find this representation right here, right? So this representation, the 1/2 zero representation, we want to keep in mind that these two guys the plus and the minus guys were independent. They were independent generators. In other words, you can't build one off of the other. You can't build any n minuses off of any linear contribution of these guys, right? So you can't make these guys off of these guys, and you can't make these guys off of these guys. So this is how they get labeled, right? So we have this is our two-dimensional representation, right? Because we're looking at these guys right here, or this guy right here, right? So we're looking at this guy right here when we say a 1/2 representation, and then this guy right here when we're looking at the 0 representation. Okay, so what does this mean? So if we have 0, that means our 1/2, or that means this guy's right here, it's going to be equal to 0. Okay, so that means, well, if this guy equals this, then this guy equals 0. So Ji equals I times Ki in this representation, right? So in this representation, we have this to be the case. All right, so now we look at the plus, the positive independent generator. This is the two-dimensional representation of the SU2 group. which is this guy. So we found out again that the two-dimensional representation was this, and so we know by definition this relationship. Well, then we have, if J is here, then we can put these two guys together and we get this, and then we get this, right? So because, and again, this here, this exclamation mark is by definition. And so then we take this. Okay, so we're going to take these two guys, just move them here, and we're going to just do a little bit of algebraic manipulation. And when we do that, we find that Ki, this generator, is equal to the negative of the Pauli matrix divided by 2, and we have this I here. Okay, so things are a little bit esoteric right now. We're just going through some algebra, but then we get to we're slowly getting to the point here. All right, so we have our Ji. Well, that equals this guy up here. Okay. Well, if Ki equals this, so we can put that into here, and we get this guy, right? So J is equal to this guy. So the boosts and the rotations in this representation are this and this, right? So this is our, again, this is our rotation, right? So not respectively, right? So because we had, if we go back up here, boosts are K, rotations are J. So boosts are K, rotations are J. So this is our rotation, this is our boost. So what this tells us is that in this representation, our generators are Pauli matrices, just with these little extra terms in front of them. And for the 0, 1/2 representation, we can do sort of this exact same thing, right? We set one of them equal to 0, we find a relationship between the generators, and then using a little bit of algebraic manipulation, which is what we did in this section here, we get these two guys. And look at this, there's really only one difference here. And the difference, again, is, well, actually, it looks like I have, the difference here is that these guys should be opposite of each other. Okay. So, and I'm going to have this up here also, right? Because so here's our rotation. Again, our rotation is an exponentiation of our generator. So if our generator down here is this guy, we just plug him into here. And we do this. So this is in this representation. In the other representation, well, it's the same thing. However, with our boosts, they're different, right? Because of this sign, the signage. The thing is that when you go through all this mathematics or all this algebra, the real difference here is going to be our boosts, not our rotations. Okay. And so what we get here, again, so in one case, okay, we say Ki is equal to I times, just keeping this, so I over 2, right? So this I times the other I, well, that's going to give us, one of them is going to say essentially be positive, the other one's going to be essentially be negative, right? Because we have positive and negative. And we have this I out here, which is going to give us a real exponential. Okay. So, I know I kind of went through that a little bit fast, but a lot of it, again, was just algebraic manipulations and then exponentiating our generators. And what we get is rotations and boosts for this representation and for this representation. So I'll just say for this representation, and this is for this representation. So I actually put this into a diagram because I think this is very useful. We started off with unifying our generators that act on space-time. So I'll actually write that here, space-time operators. We can think of them as space-time operators because, again, they're 4x4 matrices. They act on 4 vectors. Operators. And then we have then this sort of, so this broke down into two different representations, right? And then both representations, again, had similar rotational rotations, but their boosts were opposite to one another, right? So these representations, this sort of begs the question, what are we going to write here? Like if these guys are space-time operators, what are these guys going to operate on? Well, the answer to that question is they're going to shift around entries and spinors, right? So these guys are operators on spinors. I'm going to put operators in quotes because this isn't really a term that's used very frequently. But I like to think of them as that, right? So these are the things, these Pauli matrices, again, are things that act on spinors. So let's just do an example. So I have an example here. And the example is we're going to boost a left chiral spinor with just I being 2, right? So I not being the imaginary number, but I being the type of Pauli matrix we are going to use. And you can do this for any Pauli matrix, but we're just going to do this for I equals 2, just as an example. Right, so here's our rotation, or actually we're doing a boost, right? So boost, and we're doing this for a left chiral spinor. So the left chiral spinor, again, is going to be this guy, left chiral spinor, and this guy is this is the right chiral spinor. We're doing this on a left chiral spinor. We are identifying the Pauli matrix, okay, and the divided by 2 thing, this is really just a constant. I'm just going to focus on the matrix for right now, and then you could put the constant in later if that's something you want to do. This is just to keep track of less stuff. So the first thing we want to do, we want to identify some powers of the matrix, and when we do that, we find out what the pattern is, right? So we do exactly that. So that's this. Right, so this matrix times itself, that's that squared, and the same matrix, but times this guy, right? Because, so this here is squared, right? Okay, and then we find out, again, that this is the same as this, right? So the pattern just repeats itself. All right. So we now say, again, I'm sort of ignoring this 2 here. You could put it in later. But so to the first power, or to the 0th power, first power, so this is a Taylor expansion. We really want to get comfortable with Taylor expansions because they're really, really important. Because they sort of bridge the gap between exponentiating something and exponentiating a generator and getting a rotation out of it. And rotations are the things we are more comfortable, at least I'm more comfortable looking at, because they make more sense, right? A matrix to me, something that I can sort of visually sort of understand in my brain as rotating a coordinate system or rotating a vector in some coordinate system. Whereas an exponential, when I look at that, I really kind of just look at an exponential and I don't really think this thing could rotate something. But when you go through the math and when you go through the Taylor expansion, you think, oh, now you begin to understand this is actually a rotation. But again, this is why Taylor expansions are so important. So we Taylor expand this. When we do that, remember everything to the 0th power is 1, or the identity. So this is the identity matrix. Then all subsequent terms of the Taylor expansion look like this, right? So we distribute this guy into each entry. Same thing, we distribute this guy into each entry. This guy squared again, if you remember, it was right here. And that's why we get these two guys, and then so forth. So this, okay. So this is what we get for this guy. And then putting all terms together, right? So in this entry we have 1, we have positive this guy right here, and then so forth. So that's going to be right here. And then we have this guy here. This entry here starts with a 0, so we're going to start here. That's what we're doing here, and you can see the pattern, right? So you put all the entries together into one matrix like this, and then lo and behold, this is what we see. This is hyperbolic tangent, or hyperbolic cosine and sines, and the sines being multiplied by power, or by I. And this is a boost transformation, right? So this was a boost. This was a boost for a left chiral spinor in which we use this guy, right? So when we do these types of calculations, again, this was just an example for this Pauli matrix, but when we do these types of calculations, we can experiment. We can say, okay, what does this look like for each and every one of our Pauli matrices? And I'm not going to do that, right? Because we've sort of gone through one example. You can do the same thing for the other Pauli matrices. And I would also encourage looking at this, going through this example again and summing over all of the Pauli matrices while you do this. It's going to be a heftier calculation, no doubt. However, remember the generators, any linear contribution of these generators is also going to be a representation of the Lorentz transformation. So that's all to say that these matrices, when you do all those calculations, are all going to be valid rotations or boosts for these objects that we're going to call spinors. And my apologies for the dog barking. And I think I'm going to leave it at that, because this video again is we're pushing, looks like 20 minutes here. And I think that, yeah, that's all I've got to say. I'll see you guys, if you like this kind of content, make sure to hit that like and subscribe button, and I'll see you guys in the next one. Bye.